Imagine trying to model something complex, like predicting tomorrow's weather or the price of a house. You meticulously gather every piece of data you can: temperature, humidity, wind speed, cloud cover, and for houses, square footage, number of rooms, garden size, proximity to schools, even the color of the front door or the type of mailbox. When you have a handful of features, our standard linear models perform admirably, fitting a line or a hyperplane to explain the relationship. But what happens when you have, or even, of these features? Suddenly, your model gains incredible flexibility. It can twist and turn, contorting itself to perfectly fit every single data point you provide. You see this visually as a wiggly line or a bumpy surface that perfectly hugs all the training examples. It might look impressive, like it truly understands the data. But then, you feed it a new, unseen house, or ask it to predict tomorrow's weather based on slightly different conditions, and the predictions are wildly off. This is the classic dilemma of overfitting. Our model has learned the training data, not just the fundamental. The coefficients, these numbers that tell us how much each feature influences the outcome, have become extremely large and unstable, oscillating wildly to account for every tiny detail of the training data. So, how do we rein in this runaway complexity? How do we encourage our model to be simpler, to focus on the truly important features without throwing away valuable information? This is where statistical regularization enters the picture. The core idea is beautifully intuitive. We modify our model's objective. Instead of just minimizing the error between its predictions and the actual data, we add a second component to the cost function, a penalty for large coefficients. We're telling the model, hey, fit the data well, but please, try to keep your coefficients small, keep them humble. Let's visualize this. Imagine we have two coefficients, beta 1 and beta 2. Our model's error, often represented by the sum of squared residuals, forms concentric elliptical contours in this beta 1 beta 2 plane. The center of these ellipses is where the error is minimized without any penalty. Now we introduce our penalty. Consider, also known as L2 regularization. Here, the penalty term is proportional to the sum of the squares of the coefficients, sum beta I squared. Geometrically, this means we're constraining our coefficients to lie within a circle centered at the origin, or more generally, a sphere in higher dimensions. As we try to minimize our overall cost function, which is the sum of the error and this penalty, we're looking for the smallest error ellipse that just touches this spherical constraint. On screen, as you see the contours of the error function expanding, the optimal solution is the first point of contact with our L2 sphere. This force pulls the coefficients towards zero, but rarely exactly to zero. It effectively shrinks them, making the model more stable and less sensitive to slight variations in the input data. This shrinking is particularly powerful when features are highly correlated, a phenomenon called multicollinearity. When two features provide very similar information, an unregularized model might assign large, offsetting coefficients to them, leading to instability. Ridge regression distributes the influence more smoothly among these correlated features. Now, what if we want to not just shrink coefficients, but to actually eliminate some features entirely, effectively performing automatic feature selection? This is the domain of, or L1 regularization. The lasso penalty is proportional to the sum of the absolute values of the coefficients, sum, beta I. Geometrically, instead of a sphere, our constraint region is a diamond shape, or a cross polytope in higher dimensions. This diamond has sharp corners that lie directly on the axis. When our error contours expand and touch this diamond, they are much more likely to make contact at one of these corners. And what does touching a corner mean? It means one or more coefficients are forced to be exactly zero. This is profoundly elegant. Without us explicitly telling the model, ignore feature X, the geometry of the L1 penalty inherently encourages sparsity, effectively removing irrelevant features. We're literally asking the model to build a simpler, more interpretable story by discarding the parts that don't contribute enough. But sometimes, we want the best of both worlds. What if we have highly correlated features, where ridge's grouping effect is beneficial, but we want the sparsity and feature selection of lasso? Enter. This clever technique combines both the L1 and L2 penalties. Its geometric constraint is a fascinating hybrid. It's like a diamond with rounded corners, or a squash diamond. This shape allows ElasticNet to inherit the advantages of both. It can perform feature selection, driving some coefficients to zero like lasso, while also handling groups of correlated features gracefully, shrinking them together without arbitrarily selecting just one. This makes it particularly robust in situations with many features, especially when those features exhibit strong correlations, common in fields like genomics or text analysis. These regularization techniques represent a fundamental shift in how we approach model building in high-dimensional spaces. We're not just seeking the perfect fit to our observed data, but a fit that is, and well to new, unseen information. By introducing this carefully crafted bias through penalties, we reduce the variance of our model, making our predictions far more reliable. This isn't about arbitrary rules, it's about a deep, beautiful interplay between geometry, statistics, and the very nature of learning from data. It's about finding that sweet spot where our models are complex enough to capture the real signal, yet simple enough to avoid being fooled by mere noise.